I'm Kazuo Hotate from the University of Tokyo. Title of my talk this afternoon is the recent achievement in BOCDA and BOCDR. Well, the BOCDA means the Brillouin optical correlation domain analysis, and the BOCDR is the Brillouin optical correlation domain reflectometry. Of course, I'd like to use the Brillouin phenomena. And when we use the stimulated Brillouin scattering, the system is called as the analysis system. And when we use the spontaneous Brillouin scattering, the system is called as the reflectometry. Today, I'd like to talk about these. And of course, the sensing mechanism for the strength or temperature is the slope dependence of the Brillouin frequency shift FB onto the strain and the temperature. So then by using the Brillouin scattering, we can measure the strain distribution and also the temperature distribution. So sometimes because of the double modulation, we cannot get any information. So we need the discriminative distributed measurement of strain and temperature. And the last part of my talk, I'd like to talk about the discriminative and distributed measurement of strain and temperature. Okay, my talk is concerning the optical correlation domain techniques. It's not the time domain technique. In our system, we use continuous light wave and manipulating the light wave interference nature by, for example, modulating the lasing frequency in sinusoidal wave. We can get the position-selective measurement of the stimulated or spontaneous Brillouin scattering nature. So that position, selected position could be swept by using some way. So finally, we can get the distributed information as to the Brillouin nature. And the one is the Brillouin optical correlation domain analysis using the stimulated Brillouin scattering, and the other is the Brillouin optical correlation domain reflectometry using the spontaneous Brillouin scattering. And we have realized the random accessibility onto the arbitrary selected multiple points along the optical fiber. And when we use the pulse light wave, sequential measurement is familiar, but in our case, we can get the random accessibility to the arbitrary multiple point. And the spatial resolution of 1.6 millimeter has already been demonstrated. And we are using the continuous wave, so the power efficiency is rather nice compared with the time domain technology. So we have already had the 5,000 points per second random accessibility speed, and the 20 traces of the fully distributed measurement has already been demonstrated. And in my final talk, the final part of my talk, discriminative and distributed measurement, is also shown. And this is the typical system of the Brillouin optical correlation domain analysis. From the laser diode, we have the probe and the pump light wave, and here we have the possibility to have the stimulated Brillouin scattering. But we additionally modulate the lasing frequency in sinusoidal wave. So then here, almost for the portion, we can prohibit the stimulated Brillouin scattering. But we can select one position at which we only have the stimulation process position selectively. So along the optical fiber, we can set one specific position at which we can get the clear Lorentz-shaped Brillouin spectrum. But other portions, the spectrum has already been broadened by the FM. So then at the end of the fiber, we can get this kind of spectrum data. Here we have the hill, and the top of the hill, we have here the tower, and the peak frequency of the tower is just corresponding to this peak frequency at the selected position. And this position could be easily swept by changing the FM frequency. So then finally we could get the distributed information. Okay, so this is the demonstration of the millimeter of the spatial resolution, and the nominal spatial resolution was 1.6 millimeter. And here we set the 3 millimeter tiny dispersion shifted fiber, and we could clearly obtain the abrupt change of the applied strain. Okay, this is, I think, the highest spatial resolution ever reported on the Brillouin distributed measurement. And but in our BOCDA technology, we modulate in sinusoidal waveform for FM. So then along the optical fiber, if the length of the fiber is rather long, in that case, we have the multiple selected position. So in order to measure only one the position to be measured, we additionally set the longer length of the pulse. The pulse phase, the typical value is along the several tens of meters. And by additionally using some timing switch, we could select only one selected position just like this. So by using this temporal-gating scheme, we could enhance the measurement range. By using this one, this is one of the demonstration. In this case, the spatial resolution was 7 centimeter, and total measurement range was more than 1 kilometer. In this case, the ratio between the spatial resolution and the measurement range was 14,700. Okay. And as I told you, in the time domain technology, people use the sequential measurement. But in our case, we selected the specific position along the optical fiber. So, and then change the position to get the distributed information. That means we can realize the random accessibility along the optical fiber. In this experiment, we set A, B, C, D to totally 4 positions. And then we skip A to B to C and D. So then this is the obtained Brillouin spectrum. So the tracing the peak, we could get this kind of multi-point dynamic strain measurement. This is the time axis. So then at the position C, we have this kind of dynamic strain, and at D, we have this kind of dynamic strain. So anyway, multiple trace could be obtained as a function of time. And in this case, total measurement points per second was 200. But recently, 200 is improved to be the 5,000. This is the demonstration of the 2-point random access measurement of the dynamic strain with the 5,000 points per second random access speed. Okay. Sometimes the people asked us, anyway, they would like to get that fully distributed information, but as high as the speed. So in order to solve such a requirement, the Kazuo over there invented when he was in a group, and he changed the modulation frequency onto the pump and the probe. So what happened? The selected, the measured position, so-called the correlation peak position, is automatically selected just like this. This is kind of the optical pulse, man-made pulse. So we can manipulate the speed of the pulse, and then by using the ordinary electronic equipment, we can get the rather high spatial resolution and high speed fully distributed measurement. This is obtained data. This is the distribution of the, this is the obtained data, and this is the strain along the optical fiber. This is the time axis. In this experiment, fully distributed 20 traces could be obtained per 1 second. Okay. So as for the application trial, we did the some trials. Today I'd like to show you some examples. And this is the tall building model. And here we set the optical fiber distributed sensors and vibrate with the earthquake waveform. And this is the obtained 2-point data as a function of the time. So this line means the so-called yielding point. That means under the earthquake situation, this building had a so huge strain beyond the yielding point. That means this building has already been broken or there's so much damaged. So by using the high-speed measurement, we could get this kind of information. And this is the Kazuo Corporation activity. He has made the BOCDA prototype model, and by using this one, they did their field work. And this is the man-made large pond, and on the surface of the pond, on the bottom of the pond, they use here the asphalt, and in the asphalt they set the optical fiber, and by using the BOCDA, they check the asphalt shape change. So this is the man-made strain by using this kind of equipment. And this is the measured data, also showing the finite element method calculations. These two are with agreement with each other. And this is another trial by the Kazuo Corporation. And this is the 4-point testing of the fiber reinforced concrete. And we push more and more the distributed strain becoming like this. And here we happen to have the strange shape of the distribution of the strain. And this corresponded to the tiny clock. And by using some calculation, they could get the width of the clock. And they found that the several tens of micron width of clock, so tiny clock, they found by using the BOCDA. Invisible clock is identified. So this is the basic diagram for the BOCDR technology. And here we set input light wave, and we have the tiny back reflected Brillouin, the spontaneous Brillouin. Additionally, we here use the reference light wave and combine and get the interference. So by modulating the laser frequency, once again, we could set here the specific position at which we could get the nice Lorentzian shape of the Brillouin spectrum in the electrical spectrum analyzer. So recently we applied the several technologies to enhance the function of this BOCDR technology. And by using the two modulation of the frequency, we could get this kind of the correlation peak. And this means that we can enhance the measurement range. And additionally, we use the phase modulation to the reference light wave. And by using this one, we could reduce the background noise. And totally, we could get this kind of data. And in this case, the nominal spatial resolution was 5.2 centimeter, and the total measurement range was 1,250 meter, and the ratio was 24,000. And this is the, I think, the largest demonstration in our research group. And this is the final topic. And by using the polarization maintaining fiber, for example, using the X-polarized axis, of course, we can get the stimulated Brillouin scattering. In that case, we here have the enhanced acoustic wave. And the acoustic wave is the longitudinal wave. So then we may have the possibility to have the Bragg reflection even when we set here the Y-polarized another light wave. And this is called the Brillouin dynamic grating. This was done with the Song. And this is a collaborative work. And we found that this is the Brillouin frequency shift around 11 gigahertz, but additionally we here have the another frequency difference. This is around 40 gigahertz over 50 gigahertz. This frequency difference is corresponded to the so-called birefringence of the panda fiber. So by using these two variables, and we have the possibility to have the temperature and the strain simultaneous discriminative measurement. This is the measured characteristics, the dependence onto the temperature or strain of the both two parameters, and this means by using this kind of matricial calculation, we could get the temperature strain distribution through these two data. And this is the prototype model of our BOCDA technology. This is the joint work with the Yokogawa Electric and Tokyo University and Mitsubishi Heavy Industries. And in this box, we set the BOCDA and additionally set the temperature and strain discriminative measurement capability. And this is the original data by getting only the Brillouin nature. In that case, of course, the strain and the temperature distribution could not be discriminated with each other. But by using the additional measurement onto the dynamic Brillouin grating, in that case, we could get the matricial calculation in order to separate the strain distribution and the temperature distribution, just like this. And by using this prototype model, we had the flight test of the aircraft structural health monitoring. And at the vertical tail wing, we set the optical fiber, and we could get this kind of dynamic strain and the temperature and the strain discriminative measurement. Okay, thank you very much for your kind attention.